This section is new perspectives to make use of existing health data in biobank registers, causality and observational studies. So anyone of you who would like to start with the new perspective in causality with the type of data that we have in the registers, that feels, is there possibilities with the data that is not yet used to the extent that we could use in the Scandinavian registers, you think? Are there, yes. Yeah.
So is it on, or?
Yes.
So I think one possibility is, okay, so this register data are very good, as I tried to emphasize in my speak, but also there's a lot of things that you don't know. The motivation, let's say you're interested in dropout, the motivation, what type of information the student has. Do they know that, a medical doctor, for instance, using that as an example, makes a lot more money, 10 times the money of a nurse at the age of 40 in Norway. So there's a lot of things that we don't have in the registry data. So I think that, and the motivations, etc. So I think one way to go is to match the registry data with real experiments. There could be lab experiments, but also field experiments to see how they affect. And that is possible, actually, to do those things. So I think that is one avenue that you could do. But then, of course, you have to ask for consent, etc. So,
So, Don, do you have anything? I mean, we have been discussing through our trip a little bit. Yes.
I guess my general comment is that I often find examples like these unsatisfying because if there's this discussion of how there's this no unmeasured confounding, which is the same as this unconfounded assignment mechanism, but then there's very little discussion of why that assumption makes sense. So in fact, when you adjust for these things, typically that's code for is doing assuming some linearity somewhere. So for example, in the table that was just put up, and there was a list of maybe 20 covariates in education and gender, and some of those values were missing, and missing was coded the same as being a third category. So there's a bundling, there was a muddling of whether it was really missing. Because if you're talking about your education, it's not if it's missing, not reported, it's not a third category. It's missing because everybody has an education, or everybody has blood pressure, and in treating it that way is just muddling the data. Even though it was reported that way, it shouldn't be analyzed that way. And there's the implicit assumption that everything's linear. And why should it be linear? Why should all the outcomes that you're worrying about be linear in this form? Why shouldn't they be linear in the logs of age? In fact, why shouldn't it be linear? Depending upon the outcome, it could be linear much more plausible to be linear in certain indicators. Maybe postmenopausal for women. There are all these interactions that make medical sense. If you're doing a medical study, you should be adjusting for things that make medical sense and then arguing that here's the assignment mechanism, here's a hypothetical experiment that's occurring in time. Instead of saying time-varying treatments and time-varying covariates, what are you assuming about simply what you mean by time-varying treatments is there's a sequential experiment taking place. And you first assign a treatment at time 1 based on some covariates that you have observed, and I guess you're assuming it's unconfounded. First treatment assignment is unconfounded given those in some linear form, and then there's a second treatment assignment that may depend upon the outcome of the first treatment assignment, and then it's ignorable in the sense of you're assuming it unconfounded. So really what I'd like to see is the description of what you're assuming, and not just in terms of this model or that model, because I mean no doctor knows what that means. No doctor should have, the standard terminology that's used to describe them, I think is probably just befuddles doctors. And they say, okay, I'm not going to worry about it. It's too hard. Go ahead, do it, and I'll look at the answer. So I find it unsatisfying for that reason. First of all, in the first part about mixing up missing data and a third category isn't being careful about the raw data. And the second one is not being careful about the description of what you're assuming. And to use jargon to describe it, I guess I find unsatisfying.
Mhm.
Yeah, so just to mention that a specific example, so we go into this, a lot of these details at least in the paper, so we haven't really, what I presented was sort of a simplification, but of course we are aware that this is in these issues. Okay.
So you do distinguish between missing data and a third category?
Yeah, or at least we do some sort of sensitivity analysis to that, but that's, of course, that's a problem that is mentioned of when it comes to this analysis. Yeah.
Okay, anyone from the audience who would like to raise a question? Yes, yes, please.
I work with the National Institute of Public Health with health registries.
No, I think.
And I'm also into digitalization and e-health and, well, all the stuff about that. And I'm a bit curious about you scientists, how you think about the artificial intelligence now coming up, being able to read all patient records and give you the diagnosis and the best treatment and personalized medicine and everything. So I will cite now, what does a world with IBM Watson look like? With Watson, the world is getting healthier, safer, cleaner, more creative, and even more personal. So what do you think about this? I have not, I don't know how you can prove or disprove this statement, but do you have any thought about this? The big hype going.
Yeah. I think the question is about big data. Big data, how should we treat it? How should we sort of, is it possible to draw inference, draw causal inference with the big data, and how should we go ahead? Sort of, yeah.
I certainly think there are tremendous possibilities about having big data, but there are big data of different types. And there's big data that comes from having lots of people, lots of patients. There's also big data that comes from having very few patients, but tremendous amounts of information on each patient. So I do some stuff with epigenetic data where there are randomized experiments done with 16 people where they expose them to either air that's polluted with diesel fuel or air that's polluted with, I'm trying to remember what it is now, another pollutant. And then they shove tubes down their throats for $200 each person and scrape the epithelial cells. And then for each cell, they get 500,000 genetic markers. They try to say, okay, so does diesel versus other stuff, maybe it's ozone and diesel, which leads to more changes in the epithelial cells on these 500,000 markers. Well, that's big data, but it's 17 people, and they get p-values. And the p-values that they get are 10 to the minus 80th, because they're doing so many damn tests. And then they do Bonferroni or something completely silly. And if they had any background in real experimental design, like the stuff I was talking about, factorial experiments, well, you can start contemplating how you do that, or what's the history on doing that well in factorial experiments? Because in these highly fractionated factorial experiments, you may have 20, 30 factors like the stem cells, the pancreatic beta cells. And there are things in engineering, in industrial engineering, where they do things like Daniel's plots, where you do half normal plots, look at these kinds of things. They go back to the 50s, that are so much more advanced than the crap that people are doing now. So it helps to know some history of bright people doing stuff in experimental design before you say, hey, we're going to invent all this stuff new. So the data are probably have the great potential, but you have to have some idea of how people have analyzed big data before you start just jumping in and throwing some silly methods at it. And the methods are typically very naive, given if you have a history of what's been going on for 60 years or 70 years or 80 years or close to 100 years. So I'd like people to, when they start attacking big data, to have some idea that it all wasn't invented with the machine learning people 15 years ago or 17 years ago. People were dealing with big data ideas when they couldn't do computing well, and they had to try to use their brain instead. Now people just jump into thinking that you can use the computer to solve the problem. Computers are wonderfully helpful. There's absolutely no idea about it. But your brain's a better computer.
I want to agree actually with Donald that there are tremendous possibilities in big data and machine learning and so on. But also I would caution against, sort of an overestimation of these possibilities. So there are some people who claim that, well, now we have big data, so all the causal inference problems are solved or can be solved by automated procedures, and that view is just crazy. Causal inference always remains a judgment, and always a judgment that's sort of against background assumptions, against background knowledge, having in view a certain purpose of application and so on. And this is just something that machines can't do. So again, I'm in favor of the brain rather than the machine here.
Machines don't learn. Programs can simulate learning, but the machines aren't learning, at least right now.
The possibilities to create hypotheses using big data, then, if you did make a distinction between sort of induction and deduction, so what's the possibilities with sort of induction with the big data that we have? Is that something that you could comment on?
I think that most of what's learned from big data has to be sort of viewed as relatively exploratory. And you're generating hypotheses. And then, one of the things that George Box, who's this great guy who died 2 years ago at 93, who did wonderful things in time series, Box-Jenkins time series analysis, all these fractional replication designs, really a brilliant statistician. He always talked about science as being, people too often think about statistics as analyzing one data set and getting the answer. And basically, it's a sequence of problems. You're trying to learn about the future. So experimental design, very rarely in industry do you do one experiment and you make a decision. You try to find a response surface. You try to find the optimal place on a response surface. You get the optimal kind of response. In fact, you and I spoke about this last night, in that, why were Japanese cars so reliable after the Second World War? Was that based on their incredible ability to do something? No. It was we built the Japanese industry based on experimental design. And in fact, every year the Japanese give, what's it called? What's his name again? I forget his name right now. But a prize based on an American experimental design guy for the best contribution to industrial experimental design. And one of these designs is actually called a Taguchi design, which is, you don't try to design a product to get the maximum length of life it'll live, for a car, for example. What you try to design for, you try to design that to be good, but minimize the variability. So the way Americans, and I guess Swedes, as we kid about, used to design automobiles is they tried to get the maximum length of life out of every part. But of course, that's not what you care about, really. If you're driving a car, if you have 1,000 parts, and there's a tremendous variability in how long each of the parts will last, and one of them falls apart after a week, you throw the car away. So what you want to do, you want to design a car so that they all last about the same time. You want to minimize the variability. Well, that's a different kind of design. So, and probably a lot of medical things are like that as well. If you have a device that's trying to implant an artificial knee or an artificial hip, do you want one that'll, on average, last the longest time, but sometimes it lasts a half a day, and other times it lasts 200 years? No, it makes no sense. If you're replacing both knees, you want them both to last about the same time. There are all these practical issues that have been around traditional statistics, traditional experimental design for people who really do experiments for decades and decades. And the discussion, a lot of discussion, is that we're all going to do this through propensity score weighting instead. Oh, that's so silly. I mean, I with Paul Rosenbaum invented that crap. So it has its uses. There's no doubt about it. you know, it's Horvitz-Thompson estimation that has certain uses, but understand the context and understand the other things that the great ideas that other people have had in the past years. It didn't all start with epidemiologists 20 years ago. We've been doing good stuff, and pick up the good stuff and know that. It's not just the data give you tremendous potential, and the computing gives you tremendous potential for doing things. But I think most of us must agree that the best computer we have, at least right now, is our brains, especially when coupled with computers. Computers are good at doing very repetitive things that are incredibly boring, that we get wrong all the time. That's what they should be doing. What we should be doing is the stuff, which problem should you work on? Which assumptions are plausible? And when you make arguments about assumptions for analyzing data, the people who are going to have to make the decisions are the MDs. And so I do a lot of stuff with FDA. And when they approve drugs at FDA, and I'm sure it's true at EMA as well, that the people who make they always have these committees, and the committees are comprised largely of doctors, because doctors are the ones who are going to have to live with the decisions. It's not the statisticians or the epidemiologists who patients are going to complain to if they die, or if their mother dies or father dies, if their knee stops working in a week. It's the doctors the patients are going to complain to. So they have to make the final decisions. And unless they understand what you're doing with these big data sources and understand the assumptions, it's all sort of a fraud. It's like Trump being elected. It's all a fraud in some sense. So I think that making assumptions as transparent as possible, and I think people understand when you say, we're going to assume for this data registry that the data were collected in a sequential randomized experiment, where the decisions were made in the following way, using the following variables at first, and then in time we went to the next decision, and these were the variables that were used. And we assumed that after, because it was randomized, they basically understand what in fact, they over-understand what a randomized experiment is. Doctors typically believe if it's randomized, everything's balanced. And even Fisher knew that wasn't true. That you want something that looks better than balanced, because they assume if it's balanced means everything's fine. And so that's why when you produce diagnostics on the background covariance between treatment and control groups, you should not only look at just at the main effects, but you should look at the interactions, because you're acting as if all those are balanced as well. And again, that's a place where computers can be terribly helpful, because they can look at dozens and dozens of plots. There are these plots, I don't know if you know, they're called love plots. A guy named Thomas Love, who's at Cleveland Clinic in the United States. I love these plots, but it's because Thomas Love made them up, not because I love them.
So anyone, perhaps we can, someone else who would like to ask some questions, and that is a little bit not related to the big data, so give some time to, yes, please.
Yes, I have a more specific question to Professor Rice's talk. You mentioned something I didn't really understand, something about predictive ability of biomarkers in observational studies versus RCTs and spectrum bias. But I'm sorry, I didn't understand. Can you please explain what you meant?
It's this is Jan van den Broeke who mentions this in the paper, and I'm not too sure if I recall all the specifics, but the point is just that in observational studies you get essentially a more representative sample for how these biomarkers work than in an RCT, and this is why what you find out in the observational study is better for making predictions of what happens in the natural population, in the non-experimental population, and that's the main idea.
Yeah, I thought of it like that. The reason why you get these kind of things is that when you do a randomized control trial, you want to have a homogeneous population. So if you don't want to have that sort of, then you would have the same sort of properties.
This surely is a very general problem of RCTs. Yeah. In order to secure internal validity, that we actually can clinch the causal conclusion, a very artificial population is created.
Yeah.
But then that makes it very hard to transport what we've learned to some other population, namely the population at large. So this is just a very, I mean, that particular case is an example of a very general problem.
Yeah, but it has nothing to do with randomization in itself.
No, that's
No, no. Okay.
Also, there are issues of informed consent in randomized trials,
Yes.
which automatically restrict the population to people who are willing to be randomized. And also, there are always exclusion restrictions for people who are too sick or too healthy, as judged by docs to participate in them. So it has to be a restricted population. And then if you find something there, then people start using, the United States at least, off-label. You get observational information for a larger population.
James Heckman also makes this point that, so essentially if you enter a randomized trial, you're playing a lottery, or you're being played with like a lottery. And some people don't like that, risk-averse subjects, and so they stay out of the experiment. And so because of that the experimental population is unrepresentative, because you get different degrees of risk aversion in the population.
Okay. No more general question? I mean, we are talking about, or perhaps all in this group are talking about sort of randomization or some experiment as a way to learn, even though we are thinking now about sort of observational studies. So you can think of this group as promoting randomized controlled trial the way that you are talking about identification, really. So when we have all these big registers that we have, is there a way to use the registers more efficiently by sort of having designs that creates natural experiments artificially? Is that a way to sort of proceed? What do you think about that?
I mean, like, if I may ask answer, I would be very careful with that. I think, and this is part of the pragmatic approach that I talk, or pragmatist approach that I talked about. What is essentially what we start with is the research question. What do we want to know from our data? And then we have to use a method that works in order to address just that question. But the question is first, not the method. And it's a bit like, the drunk person looking for the key where the light is. If we just say, well, we have to use instrumental variables, or we have to use this or that approach, because you will not be able to address all the questions using that approach. Very often you won't find an instrument that has the right properties in order to, get, to make the identification. So we can't use that approach in order to address, a certain question. So the research question, the purpose is what you start with, not the method.
Okay, I think you misunderstood my question, because if I have a specific scientific question, I can sort of create the instrument by sending out sort of information, by sending out letters, by influencing the doctors, for instance, in a way to prescribe a medicine in a way that create exogenous variation. So this means that the research question is in focus, but we don't rely on natural experiment. We create the natural experiments by ourselves by knowing where the variation the assignment comes from. So that is sort of, in that way, do you think that is sort of the possibilities for the Scandinavian registers to do like that in medical science?
So you're speaking about these encouragement designs, I hope.
Yes.
Yes. So in situations where it's arguably unethical to randomize the actual treatment, you can randomize encouragement to give a treatment. So in the examples that you're dealing with, you can have clinics get encouraged to use one drug versus another drug, and other clinics get encouraged the other way. One of the examples actually is in a paper that I wrote with some economists. I don't remember where it was published, but it had to do with, they were doing vaccinations for flu shots, where they sent out letters to half the doctors saying, flu season's coming up. Here are your elderly patients who we think are especially at risk for flu, and the other doctors didn't get that special letter. And it turned out that we analyzed it through a generalization of instrumental variables, because it's called principal stratification, where in fact the people who were encouraged to give the flu shot, 80% of them didn't do it. They didn't get a flu shot. So that'd be called a weak instrument. But it turned out a more careful analysis suggested that the effect of getting the letter and getting the flu shot was the same as getting the letter. For people who would always take the flu shot, the effect of getting the letter was the same as the effect of getting the letter and getting the flu shot. So it looked like there was absolutely no effect of the flu shot beyond getting the letter. So that made no sense to these guys, because this was a flu that was developed for this flu vaccine that was developed for the flu shot. So we started thinking, what the hell's going on? And it occurred, did you ever record the time that they got the flu shot? And they didn't. Okay. And so what the suspicion was that the people who were going to get the flu shot anyway got the flu shot earlier when they got the letter. And the people who were going to get the flu shot anyway, but did not get the letter, waited until they were sick to get the flu. And a vaccination doesn't work after you're diseased.
So there you see also the possibilities with the registers that we have, because we of course have the time when they get the flu shot directly in the registers, so that you can follow up the patient. Another thing that I was thinking about is sort of your presentation is the basically instrumental variables, the graph that you had about sort of the necessary requirement in order to estimate causal effects. And that is sort of, you need to have double blinding. Without double blinding, you don't have the arrow that sort of, then you don't block the arrow that goes directly to the cause. So double blinding is so essential for randomization. So randomization, we often talk about randomization sort of as the tool to solve the causality problem. But the really necessary requirement is the double blinding. And with this kind of encouragement design, you have the blinding.
See,
and you can do it on other things than pills. Yes, please.
Yeah, as I said earlier, these randomized experiments first were done in plants and animals, and then went into industry. And you don't have to blind. I mean, plants and animals are pretty dumb that way. So are little bearings and metallic parts and automobile tires. When were randomized experiments were first used in medicine? Were they used in the 20s or 30s? How did EMA approve drugs? Was EMA even around in the 40s and 50s? Probably not. FDA started using randomized experiments in the 50s, late 50s, primarily through the efforts of Paul Meyer, of Kaplan-Meier curves, survival curves. He was a big pusher for doing randomized experiments at FDA. Before that, they didn't do it. They approved drugs based on, here are my patients here and their patients. The drug company sells this, says it's good. We did these rat studies, and that's good enough. So this fact about double blinding didn't occur in the old stuff. The old literature on experimental design, classic books don't even talk about it because it's unnecessary in those classic experiments. It is necessary with human beings. It's not necessary with machines.
And it only works for certain kinds of treatment, right? So it's really great for, in an era where most medical treatments consist in a pill, then you can do that. But very often you can't. And I mean, like in applications in social science, it's just impossible, right? Because you need the collaboration of the person. So they need to understand what's going on. And so you can't blind, and so that invalidates the design. And I think medicine is actually going in that direction as well, with personalized medicine and so on, which makes it a lot harder actually to blind, I think.
It doesn't invalidate the design. What it says is the design and a valid analysis are more complicated than the naive design and analysis. What you're trying to do is separate the biological effect of a pill, for example, or a drug or a knee replacement from the placebo effect. And it's not impossible. That's not an impossible task. You just have to have a much more clever design than is currently used. But randomization still plays a really important role, especially if you care about p-values and confidence intervals, because that's where they come from. They come from over the randomization distribution. If you don't care about p-values and confidence intervals, and you just care about model-based inferences, then you don't need it. But most people care about these probability statements, and then you need that. But the designs have to be more complex than the ones that are currently being proposed, which means that they're not these silly kind of, propensity score things. They're much more complicated than that.
Okay, should we end with the propensity score? Yes. I think it's time for lunch. So we thank the speakers.